Hello everyone. In the last lecture, we were discussing about the different models of porosity, and we also discussed that in a petrophysical model, what we have in the log measurement. For example, we can measure two types of porosity, that is total porosity and effective porosity. Today, we will discuss density porosity log, and we'll discuss how this tool works and what type of porosity value we can measure in subsequent lectures. So let us start today's lecture. So these are the topic that we are going to cover today. We will discuss about density porosity logging tool, how the tool works, what is the tool measurement principle, what is the tool construction, and what is the output data of this logging tool, and also what type of correction need to be applied in the density porosity log. So, as I mentioned in the last class, density logging tool is a porosity logging tool. It is called the density porosity logging tool, but the tool output is not the porosity of the formation. The tool output is the bulk density measurement. It is going to give us the bulk density of the formation or overall density of the formation. From the bulk density, we have to infer the porosity of the formation. We can calculate the total porosity. We can also calculate the effective porosity. So, as in case of resistive logging tool, what was my tool output? The apparent formation resistivity. Similarly, in case of density logging tool, my tool output will be the apparent bulk density of the formation, from where I will calculate the true bulk density of the formation, and then from true bulk density of the formation I will calculate what? Something called apparent formation porosity of the formation. From apparent density porosity of the formation, that is phi d, I can compute effective porosity of the formation or the total porosity of the formation. So the tool measurement is the bulk density of the formation. From bulk density, we have to calculate our density porosity of the formation or the apparent density porosity of the formation, which will be converted to effective porosity or the total porosity of the formation. So in subsequent lecture, we will discuss how the tool data is converted to actual porosity of the formation. Now talk about the bulk density of the formation. The bulk density of the formation is related to what is my matrix and what is my fluid and what is the porosity of the formation. In fact, for a unit volume, I can write that rho b is nothing but it is 1 minus phi rho ma plus rho f into phi. That means the bulk density is related to porosity and matrix and the fluid density. If you talk about, let's say if a rock porosity is increasing, so if a rock porosity increasing, then the density of the rock is going to decrease and the vice versa. So what happens inside our rock? We have rock matrix, that is solid component, and we have fluid component. So if you compare the density of the fluids with the rock matrix or the solid part, gas have very low density, oil and water have density around 1. Depending upon the type of formation of water and its salinity, it can have density greater than 1 gram per cc, and oil will have density less than 1 gram per cc. Whereas most of the rock minerals have density somewhere around 2.5 to 3, or even greater than 3, depending upon the what type of rock mineral it is. So if a rock is porous, it has more porosity. That means solid part is being removed from the rock and more fluid part is being added. So since the fluid have less density compared to the solid part, obviously the porosity is going to increase, my rock density is going to decrease. Also, if water saturation is increases, that means rock density should also increase, because as we see that the density of gas and oil is less than water. So if the fluid is having more water, obviously its density of the fluid or average density of the fluid inside the pore spaces will increase. So due to the reason that the water density is higher than the oil and gas, so average density of the fluid inside the pore spaces will increase if the water saturation increases. So this way, my density log is related to the porosity of the formation. So in order to compute the porosity of the formation, what I should have the bulk density data from the density porosity log, as well as I should have information about the matrix density of the formation as well as the fluid density of the formation. So rho MA, that is the matrix density, rho F, that is the fluid density, must be known to calculate the porosity of the formation from the bulk density of the log record. So this is about the introduction of the density log, how density log works, what density log records, and how it is converted to porosity. It can be converted to porosity using this equation, but we should have information about the fluid and the matrix part. So let us go into detail about how this tool works. So this is a typical density logging tool. There is a skid or a pad on which we have a source and two detectors. One is called the short spacing detector, second is called the long spacing detector. This pad is forced against the wall of the formation. That means the source and the two detectors are in contact with the walls of the formation. So this source contains a radioactive source such as cesium 137 or cobalt 60. These two radioactive materials will emit gamma ray of medium energy. Generally, we have the gamma ray source which can provide us with a gamma ray of energy 0.662 mega electron volt. So that means source is going to emit a gamma ray with an energy level of 0.662 mega electron volt inside the formation. So this gamma ray will go inside the formation, it will interact with the formation minerals formation element and then come back to these two detectors. So these two detector is nothing but a gamma ray detector where the detector can detect the how much gamma ray is coming at the detector. So the tool is recording what? The tool is recording the gamma ray count at these two detectors. The short spacing detector, which is generally 7 inch away from the source, and long spacing detector, which is generally at 16 inch away from the source. So the tool measurement is our gamma ray count, how much gamma ray is coming back to detector. The source is emitting the gamma ray source, it is bombarding the gamma ray inside the formation. These gamma ray is traveling inside the formation, these are interacted with the formation and then coming back to detector where these are recorded. We generally have two detector, one is the long spacing detector and the short spacing detector. The earlier generation of logging tool or the first density porosity logging tool, they had only single detector. The single detector had problem with the mud cake correction. That's why two detectors were used. So these two detectors can compensate for the mud cake correction. So mud cake correction is needed especially when there is a irregular borehole. That means when the borehole diameter is not same at every depth. So especially if a zone is washed out, that means the formation have broken, it has fallen inside the formation, the diameter will increase by a large amount. In those zones, we have a very strong mud cake effect on the log data. There it is important to give a mud cake correction so that our density log data is accurate. Otherwise, what will happen if you don't have mud cake correction? The bulk density measurement by the tool will not be representative of the true formation bulk density and will have a wrong interpretation from the density log data. Now, before I discuss how the tool output is related to bulk density, because I told you that the tool record the count rate of the gamma ray. Let us first discuss how the gamma ray interaction happen inside the formation. For example, I just mentioned that the source emits the gamma ray inside the formation. So three type of interaction is possible. One is the Compton scattering, second is the photoelectric effect, and third is our pair production. So when the gamma ray is emitted inside the formation, it will interact with the formation minerals and it will continue to lose its energy. So while doing so, we will have these three interaction. The pair production will generally happen in this window, photoelectric effect will happen in this window, and the Compton scattering will happen in this window. So we have the atomic number of formation mineral or the formation element present inside the formation, and on the here we have the energy of the gamma ray. Depending upon the Z value of the formation mineral or element and the energy of the gamma ray, any of these three effect can happen. So what happens in all these three events or all these three interaction? For example, in Compton scattering, when a gamma ray collide with an electron orbiting a nucleus, so any element which is present inside the formation, and if gamma ray collide with the electron of that element, what happens is that the electron will get ejected from orbit and the incident gamma ray loses its energy. So this phenomena happens in our well logging. So the gamma ray we are emitting, it is going inside the formation. It is interacting with the electron of the different element or minerals present inside the formation. And when it's collide with the electron, it loses its energy. So with every collision, the gamma ray energy decreases and it continue to travel. Once it loses sufficient energy so that its energy is very low, then the photoelectric effect will happen. So in what happens in the photoelectric effect, when the gamma ray collide with an electron, it loses all of its energy and the electron is ejected from the atom. That means gamma ray will lose all of its energy, it will get absorbed and the gamma ray will cease to exist. So this is also happen in our well logging. The photoelectric effect will be also observed. So after sufficient number of collision, whatever the gamma ray that we have emitted inside the formation, they will get absorbed. The third interaction is our pair production. So a gamma ray when interact with an atom, it produces an electron and positron, which may combine later on to give us another gamma ray. So this pair production is not observed in our well logging. Only the Compton scattering and photoelectric effect is observed. For example, if you see in this figure, the pair production happens generally when the energy of the gamma ray is more than 5 or 6 mega electron volt, and the gamma ray energy that we emit inside the formation is generally around 0.66 to mega electron volt. So depending upon the Z value of the element with which the gamma ray collide, either the Compton scattering can happen or the photoelectric absorption can happen. We can see the photoelectric absorption generally happen when the energy is very low. When the energy is very high, Compton scattering will happen. That means obviously the gamma ray is going to collide, will have a Compton scattering, its energy is going to decrease, and when it have very low energy, it will get photoelectrically absorbed by the formation. So when the gamma ray are emitted, they are going inside the formation, they are interacting with the formation elements, they are colliding with the electrons of the formation. So if a formation have very high bulk density, that means the formation is very dense, that means formation has more material, that means formation have more electron density. So if I have a very dense formation which have very high bulk density, that means more electron will be there. So the probability of the gamma ray colliding with an electron when it is traveling inside the formation is very high. So what can happen is that the gamma ray will collide with the electron more, it will lose its energy more, and it will get absorbed by the formation more. So in a dense formation, I have high electron density, thus it means more number of collision, that means more Compton scattering will take place, that means I will get what? Low gamma ray count at the detector, because more collision will happen, the gamma ray will lose its energy more and more it will get absorbed. So less number of gamma ray will reach the detectors. That means low count rate is indicative of high density formation. Reverse will be case of low density formation. Low density formation means what? Less electron density inside the formation. Less electron density means what? Less number of Compton scattering collision by the gamma ray. That means gamma ray will get absorbed less and more number of gamma ray will reach the detector. So I will get what? A high count rate. This way, count rate is related to electron density of the formation or the bulk density of the formation. So this is the principal measurement of this logging tool. In this logging tool, we are going to record the gamma ray count, and the gamma ray count is related to our bulk density or electron density of the formation. Generally, we may take measurement in two energy window. One is the high energy window and second is the low energy window. That means we can take a record of high energy gamma ray also, and we can take a record in a window where the low energy gamma ray are detected. So high energy gamma ray window, it is related to Compton scattering, and thus it can determine the bulk density and the porosity. Whereas low energy gamma ray window, it is related to photoelectric effect and it can determine the formation lithology. For example, you can understand it this way. When the gamma ray energy is high, it cannot go in the photoelectric absorption, because for photoelectric absorption, the energy of the gamma ray must be very, very low. So whatever the high energy gamma ray count that you are getting, that must be indication of how much Compton scattering is taking place. So if a gamma ray collide with the electron formation, it is going to lose its energy. But if the energy of the gamma ray remain inside the high energy gamma ray window, it will not get photoelectrically absorbed. That means if from the Compton scattering, the gamma ray energy is going to decrease. But if we count the only the high energy gamma ray, how much high energy gamma ray are coming back to the detector, that will be true indication of how much Compton scattering is taking place. The moment you take the low energy gamma ray record in the low energy window, what will happen is that some of the gamma ray will be lost because they might have been photoelectrically absorbed. That's why the low energy gamma ray window are not used for the bulk density measurement. Whereas the low energy gamma ray window, because the low energy gamma ray can get photoelectrically absorbed, that's why they will be used for photoelectric effect or to determine the PEF values of the formation, which we can use in the determination of formation lithology. So most of the common density logging tool or the bulk density logging tool, if the tool is only designed to measure the bulk density of the formation, it will operate in the range of gamma ray energy window where the Compton scattering is taking place. That means only in the high energy gamma ray window, that is 0.2 to 0.66 to mega electron volt. So the tool responds to our electron density, because electron density controls the how much gamma ray collision is going to happen, and electron density related to bulk density, that means the tool measurement is count rate is converted to electron density, and then electron density is converted to bulk density. Then from the bulk density we can infer about the porosity of the formation. So generally the record of the tool is printed as bulk density as long space detector derived density. That means we take into account the count rate of the long spacing detector and we calculate the density from this count rate, density of the formation derived by the long spacing detector plus the correction for the mud cake effect. Some other features about this tool: logging speed is generally around 15 to 13 feet per minute. Depth of investigation is very small. It is from 3 to 6 inch inside the formation only. And vertical resolution is around 1 feet. So a note on the depth of investigation. If you can see why it is from 3 to 6 feet, this curve is short spacing detector. What we have on the y-axis is percentage of total signal coming from the short spacing detector. You can see 80% signal come from around 4 inch, and from the long spacing detector this 80% signal come from around 6 inch. That's why the tool cannot look much beyond inside the formation beyond 6 inch, because when the gamma ray are emitted and it goes inside the formation, if a gamma ray goes much deeper inside the formation, let's say gamma ray traveling deeper path, it can never come back to the long spacing detector, because it will have so many collision that it will get absorbed by the formation. That's why the depth of investigation of this tool is very, very less. So 6 inch means what? The tool is mainly looking inside the flush zone or maybe into the transition zone depending upon the depth of invasion. It never looks into the true formation. So whatever the parameter required for the conversion of bulk density of the tool to the porosity, that must be related to my flush zone. So interpretation of the bulk density to porosity requires knowledge of flush zone properties. This is a log example. We have a gamma ray log in the first track. Generally bulk density will be presented along with the correction reading, the correction for what? our mud cake, it is generally printed in the third track of the well log. In second track, generally we have the residuity logs. So we'll have a bulk density record as well as the correction. The correction for the mud cake, sometime the bulk density is converted to apparent density porosity reading. You will see the common name for this RHOB and RHOC. It's just a common name. Different companies might use different notation for plotting this log. The scale is around sometime 2 to 3 gram per cc or sometime 1.95 to 9.5 with an increment of 0.05 gram per centimeter cube. Again, it depends upon what are the density range is expected inside our formation. In this tool, mud cake correction is needed. Without mud cake correction, this tool not work. That's why when you see this correction, this delta rho is always present. This is a qualitative indicator of whether the data from the bulk density log can be used to calculate the porosity of the formation or not. In some cases, the correction will be so high that the density log data cannot be used for quantitative calculation of porosity. This delta rho or the correction for the mud cake effect is always recorded and it is much needed for our porosity calculation. For example, I have mentioned that the depth of investigation of this density logging tool is very less. Also, I mentioned that the tool is forced against the walls of the formation. So all the source is against the walls of the formation, and we also have a flow. That means when the tool is being pulled up for to take the record of the formation, it will scrap the mud cake. So most of the mud cake will be scrapped, but some mud cake might still remain the space between the source and the formation. So what can happen is that if you see the depth of investigation, the depth of investigation is very less. So even if small mud cake remains, the gamma ray first have to travel through the mud cake. That means the mud cake is also going to affect the response of our density logging tool. That's why mud cake correction is needed. That's why we are recording the data from the taking a two detector, short spacing detector and the long spacing detector. So just to summarize, why mud cake correction needed? Because if the mud cake is there inside the between source and our formation, it can affect the log reading. So we can say that the apparent density recorded by the tool will be average or weighted density of the mud cake and the formation. And this happened because my depth of investigation is very low. Now, if you look at these two figures, the first figure is record of count rate and the density of the formation. So we have two detector, short spacing detector and the long spacing detector. You can see when the density of the formation is increasing, the count rate both the long spacing as well as the short spacing is decreasing. At short spacing we have high count rate and the long spacing we have low count rate. That is expected because the gamma ray have to travel more distant in order to reach the long spacing detector, but both of them are following the same relationship. As the density of the formation is increasing, the count rate is decreasing. Now talk about our mud cake. So a gamma ray which is traveling from the source to the short spacing detector, it is following this path, and a gamma ray which is have to reach the long spacing detector, it is following this path. That means the short spacing detectors is encountering gamma ray which is traveling through the mud cake and a very small part of the formation, whereas the long spacing detector, it is encountering gamma ray which have traveled through the mud cake, but they have traveled a large distance inside the formation. So I can say that since whatever the gamma ray which is reaching here at the short spacing detectors, they will be affected more by the mud cake because the gamma ray is spending less time inside the formation or less distance inside the formation, and it is spending considerable time inside the or path inside the mud cake. Whereas long spacing detector gamma ray count is less affected by the mud cake because the gamma ray is traveling a larger distance inside the formation. So when compared to the gamma ray travel path inside the mud cake and the formation, at the long spacing detector, the gamma ray have traveled more distance inside the formation. So it will have more signal of the formation. So this way we can compare the gamma ray count at the long spacing detector and the short spacing detector to get an idea about the mud cake effect, because long spacing detector is less influenced by the mud cake, whereas the short spacing detector is highly affected by the our mud cake. We can understand this mud cake correction or the effect of mud cake with a curve which is called rib and spine curve. Let us take an example of a case where we have no mud cake. So let us compare the ideal far and near count response. So long spacing count rate and the near spacing detector count rate, they are printed on log graph paper. Then it will look something like this. Because there is no mud cake effect, then the both count rate will be what? Proportional to the formation. Because there is no mud cake, so all the gamma ray will be traveling inside the formation only. That means the count rate at the long spacing detector and the count rate at short spacing detector will be representative of our formation only. That means both the count rate can be used to calculate the formation bulk density. Now remember, the count rate at the both detector will be proportional to the our formation density because there is no mud cake, but the count rate will be different because the short spacing detector is near the source and the long spacing detector is farther from the source. So the count rate at the short spacing detector will be high compared to the count rate at the long spacing detector. So count rate is still different, but the both count rates are proportional to the formation. That's why I can expect to get a straight line. You can see also that at high bulk density the count rates are low, at low bulk density the count rates are high. So this line is referred as spine line, which is not affected by the mud cake. Now all the points on the this spine curve represents what? The response of logging tool at different bulk density of the formation. Now let us move to the real condition when we have mud cake. So this is an example of when the formation have bulk density of 2.7 gram per centimeter cube and the mud cake density is 1.5 gram per centimeter cube. That means my mud cake is lighter than the formation. So this green point is our what? This is our formation. It have a bulk density of the formation. If no mud cake is present, both the near spacing detector and the long spacing detector will read this bulk density. The moment the mud cake is present, what will happen? My response is going to change. For example, this curved response is response of logging tool at different mud cake thickness. So a small spacing detector or short spacing detector is highly affected by the mud cake. So mud cake is lighter. What will happen? So overall density recorded by the short spacing detector will be average weighted density of the mud cake and the formation, which will be less than the true formation density because mud cake have lower density. That's why near spacing detector count rate is going to increase because it is responding to an average density which is less than the bulk density of the formation. So you can see at different mud cake thickness, my near spacing count rate is increasing. My long spacing count rate or the long space detector count rate is also increasing, but long spacing count rate is not increasing that much compared to my short spacing count rate because long spacing detector are less affected by the mud cake. So this way my count rate is going to increase with the increase in mud cake thickness. So if I have more mud cake thickness along this direction, what will happen? My count rate is going to increase because my count rate or the tool detectors are looking inside the mud also, and when the thickness of the mud is increasing, the gamma ray will be traveling more inside the mud, so the mud effect or the mud signal is going to increase. So theoretically, if I have infinite mud cake thickness, that means all the gamma ray will be traveling only inside the mud cake. So if all the gamma ray is traveling inside the mud cake, that means the tool is going to record the mud cake density. So at infinite mud cake thickness, the tool will be recording only the mud cake density. So this is yellow point is my mud cake density. So green point is the ideal response when there is no mud cake, and if the mud cake thickness increases, I will have deviation from this spine curve along in this direction, which will be theoretically at infinite mud cake thickness come back to the our mud cake density. So this curve is called a rib curve. So I can have multiple rib curve. For example, this was for a bulk density 2.7 gram per centimeter cube. So let's say if I have a bulk density of the formation is 2. For that, I will have different rib responses or the different responses to different mud cake thickness, and I will have a response like this. So we can understand the effect in these three figures. First figure is effect of mud cake thickness. So that is like earlier, just we discussed, this is the effect of mud cake thickness for a bulk density of 2.5 to a mud cake density of 1.5 gram per centimeter cube. Now effect of mud cake density also, for example, this green point is, let's say, my bulk density of the formation, and if I have a mud cake density also same as the my bulk density of the formation. No matter what is the mud cake thickness, I am going to record the same density. Even if the mud cake thickness is infinite, it will read the mud cake density, but since the mud cake density is same as the bulk density, both the yellow point, that is the response of the mud cake, will always be at the same point. If I have, let's say, mud cake density here, I will have one rib curve here. If I have mud cake density here, I will have rib curve like this. If I have mud cake density here, that is 3 gram per centimeter cube. Now what is happening? Mud cake density is increasing. Then the rib curve will be in this direction, other direction. So what is happening at this point when the mud cake density is 3 gram per centimeter cube? My mud cake is heavier than the bulk density. Since gamma is traveling inside the heavier mud cake, our counter rate is going to decrease because overall average weighted density of the mud cake and the formation will be greater than the my true bulk density of the formation. That's why the counter rate is decreasing and the rib curve is on the this side. So for example, if I have buried mud cake, if the mud has buried, there could be condition that possible that the my mud cake have more density compared to the my formation. In the last figure, I have bulk density, 3 bulk density of the formation. For example, if the bulk density of the formation is 3 gram per centimeter cube, I will have this rib curve at 2.5, I will have this rib curve, and at 2, I will have this rib curve. So what we can do is that we can different a number of rib curves at different combination of mud cake density as well as the formation bulk density. For example, this is a spine and rib plot generated for a particular tool in a laboratory study, and this curve can be later on be used to provide you a mud cake correction. So now different combination of mud cake and bulk density are considered and rib and spine curve has been generated. So this could be used to get the mud cake correction. So how do we get the mud cake correction from this rib and spine curve? So what we need to do is that we need to follow this point O, that is the long spacing detector and the short spacing detector reading, and follow the slope of rib curve to go to the our spine, that is the point P. This point P is now our corrected bulk density of the formation corrected for the mud cake. So generally this record is printed in terms of, as I mentioned earlier, long spacing detector bulk density plus the mud cake correction. So what is the long spacing detector bulk density? This is this point. So this point Q is my long spacing detector bulk density, and how much correction is applied? This PQ distance, that is the delta rho, that is our correction. So this way this rib and spine curve can be used to apply the correction. Now this mud cake correction is automatically applied at the well site. The software does the calculation by itself and you don't have to do this calculation manually or even in the software. Generally it will be automatically applied and a rho ls plus delta rho curve will be printed separately. So long spacing detector bulk density will be used along with the correction to calculate the bulk density of the formation. So this bulk density of the formation, that will be your first log record along with the delta rho will be printed. So why do we need to study this? So although a logging engineer or a log interpreter might not need to apply the mud cake correction when he is interpreting the log, he will get the response of rho b and delta rho from the logging company. But my point is, I wanted to discuss this mud cake compensation in detail because you need to understand that mud cake compensation is always required, and without knowing the what is the delta rho values, we cannot know the whether the log is good, it have good quality for interpretation or for the quantity interpretation or not. That means in case when delta rho or the correction is very high, we cannot use the rho b data for quantitative measurement. It can only be used for qualitative measurement. For example, here we have two cases. The first case, the well depth here, second case, well depth here. Here what we have, the borehole diameter have increased. So between the tool and the formation, I might have mud cake or a pocket of drilling fluid. And here I don't have anything, only mud cake and then the formation. So let's say if this pocket or the borehole diameter which have increased, it's greater than 6 inch. That means what? The tool is mainly looking inside the mud or mud cake which is present inside that pocket. So I will end up measuring what? If it is this pocket is totally made of mud cake, I will end up measuring the mud cake density. So this will be identified in our correction curve. You can see the correction value is increasing like this. That's why correction curve is always presented. So generally correction value, threshold value is 0.15 gram per cc. Again, it will depend upon the tool. So if the correction is greater than 0.5 or less than minus 1.5, the tool data is unreliable for quantitative interpretation. That means we cannot use the bulk density data to porosity. In that case, tool data will be so much affected by the mud cake that we cannot infer the porosity from the bulk density data. Again, this value may vary from tool to tool. So you need to check with the what type of tool that you are using and what is the threshold values for this correction. So before interpreting the log data for porosity, we must check that what is my delta rho values, so whether we can use the log data for porosity calculation or not. That's why it is very much important to know the what is mud correction values. So today we discussed about the density logging tool principle. We discussed how the tool work, what is the tool measurement, that is the gamma ray count. The gamma ray count is converted to electron density is converted to bulk density, and we discussed that mud cake correction is very important for the density logging tool because it has very low depth of investigation, and this mud cake correction is achieved by using two detectors, one at the shorter spacing and one at the longer spacing. In the next class onward, we'll discuss more detail about our density logging tool, including how to infer the porosity values from our bulk density measurement.